What is up, young chemists? Mr. Rosen here. Today we're going to talk about pH calculations. Acids and bases is the unit that this is from. So first we're going to talk a little bit about the idea of something being acidic or basic. So as it says at the top here, the acidity or basicity of a solution can be represented using the pH scale. pH is a measure of the hydrogen ion concentration in solution. So that looks like this right here. If you have H plus in square brackets, those square brackets mean concentration. That means molarity, moles per liter. Okay. Now, if you put an acid into water, just like a generic acid, I'll write here as HA, and I put it into water, H2O, it's going to reach an equilibrium, and the acid is going to give an H to the water, and so water is going to become H3O positive, what's called a hydronium ion. And then you'll have the anion of the acid left over, and an equilibrium will be reached. Okay. Now, if we went in the reverse direction, then hydronium here would act as the acid, and it would be donating a hydrogen to this, which is our conjugate base. So this is actually what happens. To simplify the acid and its breaking down, really it's HA goes to a hydrogen ion plus the anion, right? That's happening. But because this is in water, this hydrogen immediately is going to attach to a water molecule and give you this. So measuring the hydronium ion concentration is kind of going to be the same as measuring the hydrogen ion concentration, because the increase in these comes from an increase in these. So the next sentence on here says that if you're looking at an acidic solution, you have a concentration of hydrogen ions that's greater than the concentration of hydroxide ions in solution. Okay? If the concentration of hydrogen ions and hydroxide ions is equal, that's a neutral solution. Okay? So that's kind of shown here. If you multiply the concentration of H and the concentration of OH, you get this, which is a constant. When these two are equal, you have a neutral solution, which is a pH of 7. Okay, so I'm actually just going to write this off to the side. If you have a pH equal to 7, that's neutral. If pH is less than 7, that's acidic. And if pH is more than 7, it's basic. Okay? And because when you multiply these together, you get a constant, what that means is if the concentration of H increases, the concentration of OH must decrease. So if something's becoming more acidic, it's becoming less basic. And the same goes the other way around. Okay, now you can see this pH toolbox is what we're going to be referring to, and in my class this is provided. You just need to know how to use them. It's on the useful facts sheet for our test. The pH scale is a logarithmic scale. We use a base 10 logarithm or a common logarithm, and what that means is each increase of pH by 1 represents a tenfold increase in the concentration of H. Actually, this is I just wrote this. I wrote this backwards. So what I'm trying to say is that if you have a change of 1, okay, I'll just say with a change of 1 on the pH scale, that represents a 10-fold change in the concentration of H. I kind of wrote this backwards because if you have a lower pH, it's more acidic. So, a pH of 2 is 10 times more acidic than a pH of 3. I wrote increase, and I was thinking increasing acidity, so I apologize about that. But the idea is one step on the pH scale is a 10-fold change in terms of concentration. So let's look at some example problems. Sorry about the confusion there. So the first question says, what is the pH of a 0.0002 molarity solution of hydrochloric acid? Now, part of this is recognizing that HCl is a strong acid, okay? So that means that if you put HCl into water, virtually all of the HCl's are going to break down into hydrogen and chloride, okay? So like if we put 100 of these into solution, we would get 100 of these and 100 of these, okay? So the concentration of HCl is going to be the concentration of RH, okay? So concentration of H ions is 0.0002 molarity. Now, if this was a weak acid, that means it would only partially go to ions, some percent would go to ions, and then our concentration of H would be that percent of whatever our starting molarity is. But this is a strong acid, so our concentration of H is the same as the concentration of our HCl. Now, the pH is equal to the negative log of the concentration of H. So we have to take the negative log of this number, So pH equals the negative log of 0.0002. Now, this log, what's called a common log or a base 10 log, is the log is the power to which 10 must be raised to yield that number. So when we're doing this, we're thinking 10 needs to be raised to what power to get this number? And it's going to be negative. So fortunately for us, there is just a log button on the calculator. So I can just say negative log of 0.0002, and it will give me my answer, which is 3.699. So pH equals 3.699. Now, in terms of if this makes sense or not, like 10 to the 1 is 10, right? So the log of 10 is 1. 10 to the 2 is 100, right? So the log of 100 is 2, right? So you have to think 10 raised to what power gives you that number. So the log of 100 is 2. Now we found the log of this number. So if we did 10 to the negative 1, we would get 0.1. If we did 10 to the negative 2, we would get 0.01. 10 to the negative 3 is 0.001. And 10 to the negative 4 is 0.0001. Now, this number is in between these two, right? It's in between these two. And so that means our log is going to be somewhere between negative 3 and negative 4, but because we're taking the negative log of it, the sign is flipped. So this does make sense. So to solve this problem, pH is just the negative log of the concentration of H. That's it. Next, it says calculate the concentration of H and the pH of a 2.3 liter solution containing 24.5 grams of nitric acid. So this is getting more complicated. We need to find concentration of H, and then from concentration of H, we're going to find the pH. But to find concentration of H, we need to find the concentration of this. And by concentration, I mean molarity. Okay? Now, we have liters and we have grams. Grams needs to get turned into moles. And nitric acid is also a strong acid. So let's convert. We have 24.5 grams of HNO3. We have to turn that into moles. 1 mole of HNO3. Right, so on our calculator, sorry for the glare, hydrogen is 1.01, nitrogen is 14.01, and oxygen is 48, or there's oxygen 16 and there's 3 of them, so that's 48. So we get 63.02 grams per mole. So if I take 24.5 and I divide it by that number, what I get is 0.389 moles. Okay, so we now have moles and we also have liters. If we take moles divided by liters, 2.3 liters, I'm going to get my molarity. So I'm going to take this number and divide it by 2.3, and the molarity is 0.169. Okay, now, that's not our 0.169, that's not our final answer, but that's actually one of our answers, because nitric acid is a strong acid, so this is the molarity of the acid. Because every one of these, right, every HNO3 is going to turn into a hydrogen ion and a nitrate ion in solution. Every single one of these is going to go to one of these. Whatever the starting molarity of this is will be the ending molarity of this. So the molarity of this is 0.169 molarity. So that equals our hydrogen ion concentration. Right. That's actually the answer to one of our questions. What is the hydrogen ion concentration? Now, just like we did in the last problem, if we know the hydrogen ion concentration, the pH is equal to the negative log of the concentration of hydrogen. So that means pH is equal to the negative log of 0.169. And you should anticipate, right? If 10 to the negative 1 is 0.1, and 10 to the 0 is 1, right? This is between those two. So it's going to be between 0 and 1, I'd anticipate, but let's just see. Let's plug it in and see what we get. Negative log 0.169 is, yeah, and it is. It's between 0 and 1. Because 10 to the 0 is 1, and 10 to the negative 1 is 0.1, and this number is between that. So it's between 0 and 1. So our pH is 0.772. So very acidic, right? So that's a more complicated problem. We had to take our grams and our liters and turn it into molarity. And once we knew molarity, that was our concentration of H, and from that we can find pH. We're going to continue to refer to this toolbox for the rest of our practice problems. So the next practice problem, we have a couple more we're going to go through here. This one says, what are the concentration of H and concentration of OH in a solution with a pH of 3.5? So if pH is 3.5, you can go the other way. So we were just saying that pH is equal to the negative log of the concentration of H. So if you know the concentration of H, you can solve for pH. That's nice. But now we're going backwards. What if you know the pH? Can you solve for concentration of H? And you can. You can sort of rearrange this so that the concentration of H equals 10 to the negative pH. So if I want to know the concentration of H, I can say concentration of H equals 10 to the negative 3.5. And what I get is, let's see, 10 to the negative 3.5. So I'm going to put that in scientific notation, which is 3.16 times 10 to the negative 4. And this is going to be a concentration, so it's molarity. That is our concentration of H. Now, another key relationship here is this one right here. The concentration of H times the concentration of OH gives us this, what's called Kw. This is the ion product constant for water at 25 degrees Celsius. So when you multiply these two together, you always get that number. So if you knew one of these, you can solve for the other one, right? So for me, for this problem, it's basically writing 1.0 times 10 to the negative 14 equals 3.16 times 10 to the negative 4 times x, right? That's what we're solving for. Because if you take your concentration of H and you multiply it by your concentration of OH, you get this number. So we know this one, we're solving for this one. So to solve for x, you want to get it by itself on one side of the equal sign. We're going to divide this by 3.16 times 10 to the negative 4 so that it cancels out. And whatever we do to one side, we do to the other. So we're taking 1.0 times 10 to the negative 14 and dividing it by 3.16 times 10 to the negative 4. And that is going to give us our concentration of OH. So concentration of OH equals, and let's plug it in here and see what we get. It's going to be 1.0 times 10 to the negative 14 divided by that number, and we get 3.16 times 10 to the negative 11. And that's molarity. So there it is, and from there you could calculate the pOH using this, or you could take 14 minus this number to get the pOH. So we're just going to keep chugging along here, doing some more. What is the pH of a 6.5 times 10 to the negative 3 molarity KOH solution? So this is your molarity. So it's tempting to go, okay, pH is the negative log of the concentration of H, right, and just plug this number in. Now, if you do that, right, if you do pH equals negative log 6.5 times 10 to the negative 3, right, if you do that, what you get is, let's see, negative log 6.5 times 10 to the negative 3. We get 2.19. Now, I want you to pause and look at this. If you have a pH of 2.19, that's acidic, right? If the pH is less than 7, that's acidic. But if you look at this, KOH, that's a strong base. Strong base. Okay? If you put a strong base into water, you're not going to end up with a pH less than 7. Okay? So because this is a base, this molarity, it's not our concentration of H. It's actually the concentration of OH. So what we were doing when we calculated this, right, we actually weren't doing this. We were finding POH, which equals the negative log of the concentration of OH. That's what we were actually doing. And so this is actually the POH. And the POH is this number. Now, pH plus POH equals 14. So we just solved the POH as 2.19. So something plus 2.19 gives you 14. Another way to think about that is 14 minus 2.19 is going to give us our pH. So 14 minus that number gives us 11.8. And this is our pH. And that makes sense, right? If you put this strong base into water, you're going to have a pH that's more than 7. It's going to be basic. So you need to pay attention. Just because you have a molarity, you're tempted to do the negative log of it, finding the negative log of it will give you the pH if it's an acid, but finding the negative log of it will give you the POH if it's a base. So you have to pay attention to if it's an acid or a base. For us, basically, well, pardon the pun, but most of our acids are going to start with H. Most of our bases are going to end with OH. So if you have something that doesn't start with H, it's probably not an acid. And if it ends with OH, it's probably a base. This is like an overly simplified view of acids and bases, but in our class we're keeping it to the most common of the acids and the most common of the bases, and strong acids and strong bases. So let's do a couple more. 3. Calculate the concentration of OH in a solution in which concentration of H is this number. So this goes back to that relationship that we've done already. Concentration of H times the concentration of OH equals the ion product constant for water, 1.0 times 10 to the negative 14. Okay? They are giving you concentration of H. So that means 3.72 times 10 to the negative 3 times X equals 1.0 times 10 to the negative 14. So we need to solve for X. So we're going to divide by 3.72 times 10 to the negative 3 so that it cancels. And whatever we do to one side, we're going to do to the other. So 3.72 times 10 to the negative 3. So on the calculator here, let's see what we get. 1 times 10 to the negative 14 divided by 3.72 times 10 to the negative 3. I get 2.69 times 10 to the negative 12. And this is a concentration, so it's going to be molarity. This is our concentration of OH, right? Concentration of OH is what we're solving for. Next problem. If a solution has a concentration of OH of 5.79 times 10 to the negative 2 molarity, is it acidic, basic, or neutral? So we can do this multiple ways. Just like above, we could plug this in and solve for concentration of H, and then take the negative log of that to find pH. Or we could take the negative log of this to find our POH, and then subtract it from 14. So either way will get us to the same place, right? So you could plug this in to this equation here and solve for H. And once you know H, you could take the negative log of it to get pH. And based on the pH, you decide if it's acidic, basic, or neutral. We're going to do it a different way because we just did sort of similar to that above. So a different way would be to take we're going to solve for POH. And to do that, we take the negative log of the concentration of OH. So I'm going to take the negative log of 5.79 times 10 to the negative 2 and find my POH. Okay, so if I do that, negative log 5.79 times 10 to the negative 2, I get 1.24. That's my POH. Okay, now remember, pH plus POH equals 14. So something plus 1.24 equals 14. So on here, I could just take 14 and subtract to that number, and I get my pH, which is 12.8. Based on my pH, is it acidic, basic, or neutral? Neutral is a pH of 7. Basic is more than 7. Acidic is less than 7. This is basic. But, based on our relationships and using our pH toolbox, we could have come to this same answer going multiple ways. Final practice problem. 5. Calculate the pH of the 3.3 liter solution containing 88.8 grams of NaOH. First of all, NaOH, that is a strong base. So when we find the concentration of this, we're going to be finding the concentration of OH. And then we'll have to find the pH from there. So first we need to find our molarity. So 88.8 grams of NaOH is how many moles? 1 mole of NaOH is some number of grams. Okay. Now, sodium is 22.99, oxygen is 16, and hydrogen is 1.01. So that gives us, 16 plus 22.99 plus 1.01, we should get 40, okay? So 40 grams per mole. So if we take 88.8 and divide it by that number, 40, divided by the molar mass, that's 2.22 moles. You take moles and divide it by liters, 3.3 liters, and that's going to give you your molarity. Okay, so I'm going to divide by 3.3, and I get 0.673 molarity. Now, because this is a strong base, that molarity is my concentration of OH. So similar to how we did above, I could use my concentration of OH to solve for my concentration of H, and then take the negative log of that. Or I could solve for POH just like I did above. So I'll do it the other way, okay? So we can do this multiple ways. Rather than doing how I did above, we'll just use the ion product constant for water, which is 1.0 times 10 to the negative 14. Sorry if that's a little hard to read. Equals 0.673 times something. And that something is going to be our concentration of H. So to solve, I'm going to divide by this number on both sides. Let's see what we get. I got to put this all in parentheses, otherwise I'll mess up order of operations. So sorry about that. So concentration of H is 1.49 times 10 to the negative 14. Okay. And now we can take the negative log of this number, to find our pH. So I'm going to take the negative log because it's already in my calculator, and it's going to say negative log of that number. And I get a pH of 13.8, which is what we're solving for. This is our final answer. And does it make sense? Yeah, we're adding sodium hydroxide, which is a strong base, to water. The pH should absolutely be more than 7. It should be basic, and it's much more than 7. It's pretty concentrated. A 0.673 molarity solution produces a fairly high concentration of OH ions in solution. So there's not a one-size-fits-all approach to these problems. It's really just about understanding, sorry about the bell. It's all about understanding the relationships between pH, pOH, right? When you add those two together, you get 14. Concentration of H times concentration of OH is the ion product constant for water, what's called Kw. And knowing how the pH is the negative log of the concentration of H, and you can kind of rearrange that so that the concentration of H is 10 to the negative pH. And the same thing applies to pOH, right? pOH is the negative log of the concentration of OH, and rearranging that, you get concentration of OH is 10 to the negative pOH. Understanding these and just practicing going forwards and backwards and all the different combinations and possibilities is the key to being able to do these. This has been a presentation on pH calculations. Hopefully it has been helpful. Keep up the good work. I will see you back in class.